It's okay? I just projected the point carrier section, so this scalar products become x1 minus x2 squared, and the scalar dimension and so on. Similarly here, for these guys, capital V, capital U, which become lower cases u and v. Okay, so just to give you the complete expression, u is x 1, 2 square, x 3, 4 square over x 2, 4 square, x 1, 3 square, and v is x 1, 2 square, x 3, 4 square, x 2, 3 square, x 4 square. Okay. Everything now is it's written in physical space coordinates. Okay. This is what I call these are what I call conformal invariants. Okay, and this is the next topic. So everything is fine here. Okay, this is expression. Now just move on and talk about these guys. Okay, and specifically why this would be constant now is not constant anymore. It depends on these two guys in general. Okay, everything is fine to this point.
To this point, this dependence on UV was just we haven't yet. Yes, is to come. Now the y is
the reasons to come. I just
assume that it could be.
Yeah, I just anticipate.
Okay.
So. As you can already suspect, the name conformal invariant means that those quantities are conformal invariant, of course. Pretty much like in point carrier invariant field theory, or point carrier invariant theory, whatever it is, you have that this guy here, xi minus xj, modulus square, just modulus, is point carrier invariant. Okay? The thing is, in a point carrier, let me just put the title here. Conformal invariants. That's what we call the case of point carrier invariants. And in point carrier invariance, given any 2 points, we can construct a point carrier invariant. Okay, this is the statement. Given any 2, of course, distinct points, we can construct an invariant. Okay. For example, I give you x1, x2, then I can simply construct this guy here. Okay. Physically, the picture goes as follows. We have
this module is of course the Minkowski.
Yeah. Or repeating if you have just rotation and so on, it doesn't matter. And given, just like in a plane, this is easier to visualize, given any 2 points, x1, point 1 and point 2, I can use, point carrier invariance consists of translations and rotations. So given any 2 points, I can use translation to bring this point to the origin, okay? And then I can use rotations. So this guy can say somewhere around here, Okay, I already used translation invariance, and I still have rotation invariance. So I use rotation invariance to bring this guy here. Okay, so you see that everything now depends on this distance here, which is operand. Okay, and it is invariant. Okay, given any 2 points, I can do this. Okay, I can bring one to the origin by translation, and then put the second point on any axis. Put on this axis too if I wanted. Okay. So let's do the same game on with conformal invariance. The question is, how many points do I need to have to build a conformal invariant quantity? Okay, clearly I cannot build any conformal invariant quantity with 2 points only. Okay, you can see this easily because of scaling. Okay, this quantity is not invariant on the scaling. Okay, if I scale this guy, then I just have a lambda here, and then this breaks scaling invariance. Okay, if I try to do x1 over x2, okay, then the lambda will cancel, but then I will not have point invariance. Okay, remember, point invariance is contained inside the conformal invariance. Okay, so we must have point plus scaling and plus the special conformal transformations. Okay, invariance. Okay, so we can do this with 2 points. Okay, easily to check. We can easily check that we cannot do this with 3 points either. Okay, if I had 3 points, say x1, x2, x3, I could build, say, this guy, which is a point invariant, okay, the same rotation, x1, 2, and then I can, to get rid of to guarantee scaling invariance, I could just divide this for, say, x2, 3. But then this would actually it's because I don't want to do the computation again. The trick lies in the special conformal transformation. Okay, it is just we can read the end of the lecture notes, the course lecture notes, which cover even the differential book. But the point is the special conformal transformation won't allow you to do this. Okay, even if you try to do, of course, if I try to put anything else like here, x3 or either upsells or downsells, that will break conformal scaling invariance. But this will break special conformal invariance. And the reason is, I guess I commented this on last lecture, is because special conformal invariance relates the power of the scaling. Okay, the power to which lambda scales everything else. Okay. Constraints. And then if you do this, you have to take this, apply a SCT, and then this will be like x prime 2, x prime 2, 3, and this would also be the reason why you can still use the scaling invariance, have conformal invariance 2 points only. Then this would be, you would have those factors, I guess I call them P. Okay. I have, say, B12 here, and have B23 here. Okay. And the fact is that these guys do not cancel. Or this one. Okay. But the reason I don't want to do this is because I guess I call it B. I remember it was the second lecture. And the reason because I don't want to do this because it's B and it's just a big thing, and I have not done this. I have not prepared it. Okay. But the result is you cannot because of this you cannot construct conformal invariants with 3 points only. Okay. The thing is, you can I erase this? Can I erase this? I know just I want to give you the physical picture just like this. Okay? Make things a bit clearer. X1, X2, let's write 4 points now. And again, I'll just tell you the result that this time you can construct conformal invariants. You can, in fact, construct 2 conformal invariants. Just these ones here. Okay? I wrote that. They're called U and V. Okay? You construct the U and V. They are defined over there. And the reason now is, if you look to them, okay, they are all made up of difference between quadrants, so they are point invariants. They are clearly scaling invariants, okay, because I have 2 powers along the here, 2 powers along the downstairs too, so it cancels. And the dx from the special conformal transformation will also cancel. And the trick or mnemonic, whatever you want to call this, is that in order to have SCT invariants, I must have the same number of how to put it. What I tried with 3 points was, for example, this. Okay, point 2, 2, 3. Okay, I have 1 up here, but I need, in order to have special conformal invariants, I need to have 1 downstairs too. So with 3 points, the choice would be to go with something like this, 1, 3. But then this will spoil the scaling invariants. Okay, and the same thing for 2. Okay, the 2 you would have a special conformal invariants for the point 2. But you only have 4.3 as well. Okay, if you try to replicate this upstairs, the only option you have is 1, 3, but then cancel. So you see you cannot construct. Okay? Whereas here for 4 points you can construct this. Okay, you have 1, 2, 3, 4. Have 1, 2, 3, 4. Okay, it's the same here. 1, 2, 3, 4. 1, 2, 3, 4. Okay, it's just different permutations. Okay, this is in the end of the computation. If you choose to do that computation explicitly for the special conformal invariants, this is what usually comes down to. Okay.
For example, in both of those cases, we have x1, 2, both u and v. But,
in the numerator.
Yeah.
Yeah, the numerator. The denominator differs.
Yeah, but if we had something like x1, 3, x2, 4.
In the numerator.
Yes, but instead of the.
And then change the denominator.
It's like v over u over v is also a conformal invariant. Or not?
Yeah, it could be. But the point is a conformal invariant that is built from these 2. Okay. So it is not independent. Okay. Of course, when I say key construct, implicitly meaning independent conformal invariants. Okay. But since you touched on that point, there is remember that this construction, these guys that flew out here and played this game was a choice. So the point is, you can come across different UNVs depending on what you are reading. What is always true is that given 4 points, you have 2 conformal invariants. Okay, and I'll just tell you why. But what they actually I can change. Okay, depends how you play this game here. Okay, so you can could have different things here. As long as again, in order to guarantee special conformal invariants, a given point must appear the same number of times upstairs and downstairs. Okay. So. It is clear, right? Okay. And let's give you this picture here. Say I give you any 4 points. Okay. Then again, I can use translation to bring one of them to the origin. Then, given the origin, I can use a special conformal transformation to send one of these points to infinity, this is the hardest part. Okay. Everyone remembers that special conformal transformations can send points to infinity. One way to think about this is just because it is an inversion conjugated translation. Okay? But I don't know, when people give this argument, they usually go for the inversion, but I'm going for the SCT because inversion is not necessarily symmetry of field theory, okay? Because it's not connected to identity and so on. Okay? So the point is, you can choose a specific B. Remember the SCT had the parameter d mu. And so it has something on the denominator like this. Okay? And you can choose a B such that this guy at the denominator is 0, so you map to infinity. Okay? And if x is 0, then this guy is, okay, for the origin. This guy is 0, and whatever was up here was x mu plus x squared b mu. And this was the finite. This was the finite special conformal transformation that we discussed in the second lecture. So you see that the origin is indeed preserved by the SCT. But I can just choose any of these 3 points and choose a B such that this point will be mapped to infinity. Because I will just eliminate this denominator. Okay? So, okay, got rid of this point, say, and this guy came all the way here to infinity. Okay? So I already fixed 2 points. I used translation, and I use SCT. I still have rotation and scaling. Okay, so I'll just use rotation now to bring any one of these points here to this axis. Okay, I don't know where on the axis this point is. Okay, but then if I use scaling, I can say bring this point to 1. Okay, I choose a lambda such that this point is mapped to 1. Again, rotation preserves the origin. Okay, I'm doing rotations around the origin, and of course infinity is preserved by rotations, and then again, both the origin and infinity are preserved by scalings. Okay, so I use that. And this point, these 2 last steps will say come from here to somewhere here. I don't know, stuff like that. And this guy just came down here. Okay, so what did it do? Okay. We had a d-dimensional space here. We spoke to have more axes here. And I managed to bring any 4 points in this d-dimensional space to a plane. Okay? And I know the exact position of 3 of them. One is sits at the origin, one sits at 1, and the other one has been blown up to infinity. The only one I do not know where it lies is this point, but it lies on the plane. Okay, so it has 2, say, degrees of freedom. It has 2 unknowns. And these 2 unknowns are precisely encoded in this conformal invariant. This is the reason why we have, even any 4 points, we have 2 conformal invariants. Okay?
Why is that point in the plane? This point is in the plane.
Okay, if I have more dimensions here, this point will lie somewhere around here.
Okay.
But when I do the rotation, I can just fix a point. Okay. It need not be this plane, it be this plane here, for example. Okay.
Fixed plane.
It doesn't necessarily need to be say a plane from the coordinate made from this coordinate axis. There'll be a plane here, and then there'll be the origin here. Of course, there'll be a 1 in this line and infinity and so on. Okay, this is just for simplicity. Okay, but the point is it will lie on a plane, and this is 2 degrees of freedom. Okay. And this is again, just to conclude, precisely what these conformal invariants are. Okay. Again, you can have 5 different conformal invariants, but the point is there will only be 2 of them for 4 points. If you go to 5 points, you have more conformal invariants. I guess given say n points, believe you have something like this. 4, 4, 2, 5, 2. Okay, if you have n points, you can build n times n minus 3 over 2 conformal invariants. Okay? And I'll just leave it as an exercise for you to think about this if you want. You don't actually need to do this, or you can just read the notes. Okay, and just the last thing is okay. This is the reason why this guy did this would-be constant can depend in general on these two conformal invariants. Okay, because when I reach 4 points, I can always have these two conformal invariants. I can always have U and V. Okay, conformal symmetry won't tell me anything about U and V. Okay, so I can have any functional dependence on U and V on the 4-point function. Okay, so that's the reason that structure constant in the 3-point functions became a function itself of these two variables.
Just okay, but I could. So there must be something because I could just define now this v over u to the power of e into new constants c134. So why do I need the separation? So there's still
Oh, okay. Well, then this was the next thing.
Oh, okay.
Then you just take all this and just call everything say an f of u and v. Okay, and this is what is we call a conformal block. Okay? It doesn't matter if I have a C123 here or b over u to the power of b. I don't know what any of this is, so I just call it a f of u and v, just a generic function of u and v. And then again, conformal symmetry can tell me anything about this function because this function is unrestricted, because it is built from conformal invariants. Okay? So, is it clear why this guy that I call C123 4 can depend on U and V in general? I just put this at the start for pedagogical reasons, okay? Because I've been doing this for the 2-point functions and the 3-point functions. Okay? But it turns out to be an actual function of these two variables. Okay? And so what did we learn? 2-point functions are completely fixed by conformal invariants. 3-point functions, their functional form is completely fixed, just Power laws. Okay, we just don't know a constant that we call the structure constant. And 4-point functions, we can even determine the functional form. We can only be assured that we can factor out some power law behavior here, but then we are also left with some function here and we do not know anything about by conformal symmetry alone. Okay? By the same reason that I told you that the structure constant of 3-point function can be determined by if you have dynamical information, then these conformal blocks are also determined through dynamic information. Okay, so it depends on the specific theory. And the dependence is there is a non-trivial relation between these conformal blocks and the structure constants. Okay? This we will learn on when we discuss the operator product expansion on CFT. Had a question? No? Did I answer a question along the way? Okay.
No, so on this conformal blocks, now is when you would use like crossing symmetry to impose some more constraints, or
Yeah, there are more constraints from conformal symmetry for associativity or crossing symmetry. This we'll discuss on the when we discuss the operator product expansion. But the origin of this what they call the crossing symmetry is just again because this choice was an arbitrary choice. I could have chosen to pull out any two factors here, any other two factors and do the same game, then I'll probably define different u and v's than these ones, and it is just a choice, okay? So they must correspond to the same physical quantity, this correlator. And by requiring that they are equal, you can derive new constraints, okay? Besides this constraint from the choice of how I play this game, there are extra constraints from the dynamics on the OP. Okay? We come to this in 2 lectures, I guess. And just, I'm not going to prove any point in this lecture, but I can give you the reference. These conformal blocks, I'm going to erase this. I'll leave this. These conformal blocks are hypergeometric functions for even dimensions. And even dimensions I mean time and space. Okay. And the source for this is this was in 2000s, at least the first version of that paper. Okay. And so that's the reason why usually you're just reading some text on conformal theory and you're playing this game with conformal blocks and everything is actually for simple enough theory, just simple expressions, and then the guy just goes and say, okay, let's expand this simple function in hypergeometrics. I say, this guy has gone mad. Okay, well, why would I do this? And the reason is this has been proven. These conformal blocks are actual hypergeometric functions. And the way they prove this is they prove that the eigenfunctions of the eigenstates in a CFT are hypergeometric functions, okay, in either dimensions. For all dimensions, we have some further relations, but I'm not sure if there is a close analytical result in terms of non-functions. And the way they did that, they use the Casimir operator. Okay, just take a look at this paper, but this might involve some techniques that we'll discuss in the next few lectures. Okay, so you might not be able to understand this completely right now, but you'll soon be able to. Okay, and I have not discussed the Casimir operator, so I might just start the next lecture with that. Okay, you complete the Casimir operator starting from the light conformalism, because it's just we start from the Casimir operator for the rotation group SOD, which just J squared. And then we just see what that means in terms of the physical space conformal generators. Okay? And I guess that's everything. Let me just check. Okay, that's all. And just something I've been forgetting, just two further references that I promised you the first 2 lectures and I forgot. In the first 2 lectures, I told you that if you have free particles, actual free particles on a CFT, then they must decouple. They must be. If you have 2 massless particles in any CFT, they must be necessarily be free. And the source for this. This you can already understand simply by playing the generators of performance that we discussed in the second lecture. Okay? Just anyone is curious about it. This was due to binary in 2012, I guess. And the title is this assumption here that is discussed more broadly in this other one. So this one I haven't actually read. I don't have the title, but it's by Mori and Washington. That they show that if the scaling symmetry is spontaneously broken, then this statement that massless particles are free is not true anymore. If the scaling symmetry is spontaneously broken. Okay? Just doesn't have anything to do with this lecture, just something that I promised you in the first lecture and I just now remember. Okay? If anyone is curious to see the proof. This proof is actually very straightforward. Okay? What is may not be so straightforward, understanding this one. Okay, this he proves on the appendix, which is more than half of the paper. But given that you accept what this means, whatever this means, that he tells you in the beginning of the paper, that the proof is just like a 5-minute proof. If you have free particles. If you have massless particles, they are free. Okay, and then if you have if this case is spontaneously broken, then this might not be true. Okay? This is the discussion of the second one. Okay, and so if there are no questions, that's the end. So questions? No? Okay, so that's it. Thank you.